morning, guys. Today we will be proceeding with our discussion on eccentrically loaded columns. And it is very important to understand first what the balance condition is all about before we can take off the computation on the moment capacity of columns. So I have told you last time that before we start any computation on eccentrically loaded analysis, we have to determine first the location of the plastic centroid. But for some situations wherein a section is symmetrically loaded and symmetrically reinforced, the section is symmetrical and it is symmetrically reinforced. The location of the plastic centroid falls exactly at the geometric centroid. Okay, so that is if the concrete section is symmetric about the axis of rotation, and the reinforcement are placed symmetrically, then the location of PC is the same with CG. Okay, the center of gravity and the geometric centroid are just, of course, the same. Okay, so for this particular problem, we can take note that the location of centroid is somewhere just maybe this is the geometric centroid, so that's PC, which coincides with the geometric centroid. So if we take one half of 500, so this is just the value of xp there, which is the same as this one. Okay, so this is automatically a 250 millimeter. So wait for a moment. This is a figure that represents an actual uh, behavior together with a uniaxial bending. Okay, so our axis of bending is now this line which passes on the plastic centroid. So this is now your axis of uniaxial bending, or simply bending. So if we assume a force PB, so this is simply your axial load at balance condition, we can analyze the behavior of such column section at balance condition. Of course, we can now determine where is your eccentricity. So the eccentricity is coming from the distance from the plastic centroid up to the force. Okay, so this is now your uh, eccentricity E sub B. And the moment is simply given by a force times distance equation, which is PB EB. Also, we have to identify the location of the reinforcement at each layer of bar or level of steel bars. And we have here, in terms of the axis of bending, two layers. So we have here a layer 1, okay, from the centroid of that bar, and a layer 2 from the centroid of that bar. So we tag this now as your distance from the compression fiber. So this is now the extreme compression fiber. So from the compression fiber, there is now a distance of 65 millimeter, which is actually your D1, and 45 millimeter, which is actually your D2. Okay, so we have only a two layer of bar to consider. So later, if we do a multi-layer analysis, we can tag the layers from 1, 2, 3, 4, and so on. Okay, so this is a two-layer reinforcement. So the illustration or the representation of your strain and stress diagram is the same with that of the beam. Okay, so this is just the same as the beam, wherein the concrete strain and compression ultimate is given by this value, and the steel strain is given by this value here. Okay, epsilon S1. This is actually epsilon S1 and epsilon S2. Okay, but for balance condition, we need to remember that there is simultaneous crushing and yielding of concrete and steel respectively. okay, at the extreme compression and tension fibers. So this is automatically epsilon y. So the steel here automatically yields at balance condition. Okay, it's only at the balance condition that this is fairly automatic, because there is simultaneous crushing and yielding. So at balance condition, epsilon S2 is always epsilon Sy, and but epsilon S1 may or may not yield. Okay, so remember that. Okay, for the stress diagram, everything works the same as that for a beam. You have here a CC, which is simply equal to 0.85 FC prime A times B. So this will now be your B. And your D will become your D2 here. The effective depth is the largest D on the layer. Okay, so CC will simply be equal to 0.85 F prime C, or FC prime A times B, where A is equal to beta 1 CB at balance condition. So beta 1 is actually 0.85 for FC prime less than or equal to 28 megapascal. So when beta 1 is no longer, when FC prime is greater than 28, use the formula. There's a formula I gave you in beams which is the same with that of column analysis. Okay, we consider now the figure above, in which the force PB is acting at a distance away from the plastic centroid along a horizontal axis. So the column is then subjected both to an axial compression and a uniaxial bending moment about the vertical axis, passing at the plastic centroid of the section. So the stress and the strain diagram shown is the same stress diagram for a beam subjected to a bending moment. So we may consider analyzing the section using equilibrium and compatibility relations. So to derive the formula that we are going to use with our eccentrically loaded columns, we can use first the equilibrium equation, in which we sum up all the forces vertically equals 0. So what are the forces? We have only three forces involved here. One is CC, C1, and T2. Okay, so we have here, assuming a downward force a positive, so this becomes a PB, by the way, is here. No, I forgot to show you that PB is the force. Okay, so this, if we project this downward, so you have a downward force of PB there. So these are positive PB, negative CC, negative C1, and positive T2. So this is your summation forces of vertical equals 0, in which we can solve for PB equivalent to CC plus C1 minus T2. Okay. If we take note of the summation of moment PC equals 0, assuming a clockwise direction as positive, So we have here now your point PC. Okay, exactly that. So we have here your PC. So this PB becomes a positive clockwise. This is a negative, negative, and all are negative uh, T's. Okay, so we now make use of this. PB times the eccentricity minus minus and minus means they are all counterclockwise. So the distance from the force CC to the plastic centroid is simply given by your XP minus 1/2 of this A here. Okay, so this distance here is XP from here to there. You subtract 1/2 of A, so you get this distance here. Okay, so this is XP minus A over 2. Okay, and so is true with this distance C1 to the plastic centroid. It's simply XP minus D1. Okay, and for your T2, it's XP minus D2 or D2 minus XP. So you will find a negative uh, a value there. So you can interchange this. Okay, so T2 is D2 minus X2, XPN. Okay, if you use a negative sign, T2 must be minus. If you use a positive sign, this is correct. Okay, so it's quite confusing. I will show you a better way of dealing with this later. So note that MB is equal to PBE. And hence MB is equal to CC. This one now becomes MB. CC XP minus A over 2, C1 XP minus D1, plus T2, this must be D2 minus X2, XP. Okay, so it's a little bit confusing to use a manual way of looking into the direction of the moment, but there's a way on how to figure out that accurately by using a systematic procedure I'll show you after this. So the eccentricity E now is computed as the balance eccentricity EB and may be obtained by simply dividing MB by PB. So your EB here is simply equal to MB over PB. Okay, so if you remember illustrative example 1.6 that I gave you in the board problem, I think these are board problems. So we can now solve it, no? So this can now be uh, addressed since we already know what balance failure is all about. Okay, so let's try solving it. So a 300 millimeter by 500 millimeter column is reinforced with 428 millimeter diameter bar. The area of each bar is 615.75 square millimeter. which are placed one in each corner as shown. So the concrete cylinder strength Fc prime is 24.19 megapascal, and the steel yield strength is 345.58 megapascal. So the modulus of elasticity of steel is fixed to 200,000 megapascal. So which of the following gives PB, which of the following gives MB, and which of the following gives EB? So this is now a problem on the concept of balance failure condition, okay, or balance condition. So I use a math guide here, so I take the given values 24.19, 345.58. So these are directly given, okay. Also your B is directly given, your AS1 is solved, AS2, and this part here are taken from the figure, but it's a little bit tricky, you know? Okay, so your D2 from the figure is 435, there you are, and D1 is 65. So you always refer your D1 and D2 okay, so your reference is the compression side, okay. So beta 1 is 0.85 because Fc prime is less than 28 megapascal. So if beta 1 is greater than 28, then you have to compute for beta 1. Okay, solution. We now use a very uh, familiar equation. So this is a beam equation. So always this is the extreme tension refer to the extreme tension bar. So the last, okay, the last reinforcement at the tension side is the one that is used in the formula. So for beam equation, we only have one extreme tension bar, so we don't have to worry about it. But here, sometimes we have a couple of tension bars layer, no? That we have to work on. So after solving for CB, you can now get your A by solving your beta 1 CB here. Note that the steel yields in tension is automatic. No? So for balance condition, this is automatically drawn. But for unbalanced condition, this must be checked. Okay. For the steel in compression, always, whether it's balanced or not, we have to check if the steel yields in compression by using this formula here. Okay, so 600 CV minus 65 over CV is equal to 458, which is greater than 345. Okay, so this is greater than 345.58. So this is yielding. So your CC can now be computed on the basis of 0.85 FC prime AB. So you get here 1447 kilonewton if you want this to be kilonewton, because the unit here is in newton. Okay, so everything is now just a matter of applying the equations we have derived on top. So C1 is AS1 FY is 4256 because it yields, no? If the compression still does not yield, you use Fs, okay, Fs1. So this is automatically also yielding. Uh, we are assured of yielding. Okay. So for the balance condition using equilibrium equation, so this is on the basis of equilibrium on top. We have PB is equal to CC plus C1 minus T2. You get now 1447 Newton. Okay, so if we want to convert it to kilonewton, this is 14.7. Automatically, this just cancels out, class, because they are the same, so this just cancels out. And for MD, we just follow the formula a while ago on top. So this is, remember, this is D2 minus XP. If you use a negative sign here, you can use an XP minus D2. So other books uses this one here. Okay, so I'll show you again later how to deal with this without thinking a lot about it by using a systematic procedure. So MB is now 3495 times 10 to the 8, or simply this is 349.5 kilonewton meter. Okay, and EB is simply obtained by dividing MB and PB. There you get 241.496 millimeter. So this can be checked. The answers can be checked on the lecture I gave you last time. And they are not the same, but they are very near to the answers given there. Okay, so we will be we are now getting near to the analysis. We're just on the balance condition. So on the next topic, I will be giving you the procedure on how to analyze columns if the condition is not the balance condition, for us to be able to address all possibilities in the column analysis. Okay, thank you very much for listening. I'll see you on the next video.